Hello friends, hope you all are doing well. Hope you are staying on top of your schoolwork, but also finding other outlets to be creative and just exercise your brain in various ways. This is a screencast of me playing on Procreate, which is my new creative outlet. So I hope that you are finding ways to both create and serve and do things that you enjoy and that give you joy and peace, and hopefully maybe give back to people a little bit as well. So this is my current obsession, and yeah, just wanted to share a bit with you before we get started here. So welcome back. We are actually on our final review topic for FRQs, and this is, differential equations. So our next Zoom for our cold FRQs will be Monday at 1:30, and that leaves us exactly 2 weeks before our AP exam. So that is going to be crunch time. Expect to see a few different things at that point. We are going to be kind of putting all the topics together, and you're going to be getting lots of mixed practice. That's Jonas in the background. So again, this is our last topic, and then we'll be putting it all together. I've created a mock that you'll take, and I have another teacher friend who's created a different mock. A little bit different because this is not from College Board like our typical mocks are, but we're doing the best we can under the circumstances, and I think that they are good representations of close to what you will see. So let's start with topic. This is topic, I think, 4 since post-spring break, 5 if you count area volume. Before we get started here, I do want to do a quick integration review with these because they all look kind of similar, but obviously they all have different antiderivatives. So integral of 1 over x dx means find all antiderivatives of 1 over x. In that case, it'll be ln of the absolute value of x plus c, right? Because the derivative of ln of x is 1 over x. We throw the absolute values around because you cannot take log of a negative number. Okay, now the second one is not, however, ln of x squared, right? Because the denominator is not linear. So what can we do here? We can rewrite this as the integral of x to the negative 2 dx, and now we can go ahead and antiderive. So bump the power up by 1, and then divide by your new power. Don't forget your plus c. All right, what about that third one? Is that going to be an ln of x? It will, because look, your denominator is linear. So we're going to do kind of an anti-chain rule here. So antiderive the outer. I know that that's ln. Hold the inner. Now we're anti-chain ruling, so divide by the derivative of the inner instead of multiplying. So again, that yellow piece that I highlighted, that's your inner function. Derivative of 2x is 2. If I want to divide by 2, that's the same as multiplying by a half. Okay. Similarly, for the last example, I can see that the inner function is linear. So I'm going to antiderive the outer, hold the inner. Now divide by the derivative of the inner, which is negative 1. All right, so a quick little antiderivative review there for you, especially involving ln of x, because those pop up a lot with differential equations. All right, I'm doing the first problem with you. This is the problem from your train set looks awesome, Jonas. From 2012, question 5. To me, this was one of the harder ones that we've seen in the past few years, so that's why I'm doing this one with you. So let's read. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams at t days after it's first weighed, then dB dt is 1/5 times the quantity 100 minus b. Let y equals b of t be the solution to the differential equation above with initial condition b of 0 is 20. All right, part A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain. Okay, well, what gives us how fast something changes? That would be the derivative, right? So I just want to evaluate the derivative, dB dt, this guy, at 40 grams and at 70 grams. And remember that B is the weight of the bird in grams. So I'm just plugging in 40 and 70 for B and seeing which one is bigger. Okay, so when B is 40, dB dt is 1/5 times 100 minus 40. So 60 divided by 5 is 12. Now if I do the same thing but for B equals 70, I have that dB dt is 1/5 times 100 minus 70, which will be 6. Okay, so my derivative is faster when the baby bird weighs 40. I'm sorry, my derivative is larger when the baby bird weighs 40 grams versus 70 grams. So that means that the bird is gaining weight faster when it weighs 40. So 40 since 12 is larger than 6, and we said what 12 was and what 6 was, right? That was the derivative at 70 and 40 respectively. All right, part B, find the second derivative in terms of B, and then use the second derivative to explain why the graph of B cannot resemble the following graph, so the graph they have below there. Okay, so let's find d to b dt first. So they already gave me the first derivative, so I'm going to come up here and take the derivative of that with respect to what? With respect to t. Always look at the denominator to know. So I have 1/5, that's a coefficient, it's going to come with me. Then I've got 100 minus b. Well, the derivative of 100, a constant, is 0. Then minus the derivative of b with respect to t is just going to be 1 dB dt, right? So that's our second derivative in terms of dB dt, but look, they wanted it in terms of b, so I'm only allowed to have b as part of my answer, not t. So what can I do? So far I've got negative 1/5 dB dt, right? Well, take a look at what I boxed. I can make that substitution for dB dt, correct? So I've got negative 1/5. Now for dB dt, I'm substituting this in, so I've got 1/5 times 100 minus b. So if I simplify a little bit, I've got negative 1 over 25 times 100 minus b. Okay, so there's the second derivative in terms of b, and then we're supposed to use this to explain why the graph of b cannot resemble the graph below. Well, let's talk about that. What does the second derivative, the sign of the second derivative, give us in terms of the graph of the original? Gives us the concavity, okay? So take a look at, remember your y-axis is b, right? So look here, b is going from 20 to 100, right? So if b is going from 20 to 100, then the stuff in parentheses, the stuff here, would always be positive, right? You've got a positive times a negative, so the second derivative is always negative, meaning the graph should always be concave down, which it's not, right? It's concave up and then concave down, okay? So for b between 20 and 100, like they've given us, the second derivative with respect to time is always going to be negative. So the graph of b should always be concave down. Okay, and that's that. Now I do want to pause a little bit here and kind of stray from this problem a bit because I really like this graph in terms of what we are going through right now as a country. So this is actually a logistic curve, which is typically the kind of curve you'll see that models the spread of viruses. What we call 100, this is, you can tell it's an asymptote here, that's called your limiting factor. And typically your limiting factor for a virus starts out as the size of your population, right? Because you can't go any farther than that. You could, worst case scenario, infect everybody, but you can't infect more than the people you have available, right? Right here, right around there is your inflection point, right? So an inflection point is when the given graph changes concavity. It's also when your derivative, your slope, is at a max or a min. So you can see right there is your steepest part of the graph, and then your slope switch to actually sitting above the curve. Okay, so we care very much about inflection points when we're talking about the spread of diseases because we need to know when does the disease start to slow down, okay, and that's at an inflection point. Now, let's come back to that asymptote, that carrying capacity. You've heard it said that we want to flatten the curve, right? So we're trying to bring that asymptote down. How do we do that? Well, we reduce the number of people that can possibly be infected by social distancing, okay? So that is a little bit of the calculus behind what we're trying to do here. Thank you, baby bird problem of 2012. Okay, part C. I brought that differential equation back up. It says use separation of variables. So separate and integrate to find y equals b of t, the particular solution to the differential equation with initial condition. All of these are keywords that tell us we need to separate and integrate. So actually solve the diff EQ, right? So step one, separate. I do want to remind you that they're using t for your independent variable and b for your dependent variable right now, okay? So really make sure you keep that straight because we've got to, step one, separate our variables, and we have to separate them correctly. So I'm going to keep dB in the numerator. I'm going to go ahead and bring that whole set of parentheses over. Remember, just by kind of multiplying or dividing here. In this case, I need to divide, so it's going to end up in the denominator. I'm going to go ahead and keep the 1/5 on the right-hand side. You could have brought it over. I think it complicates things a little bit. Simpler is better. And then we do need to bring the dt over. Okay, so that's step one, separate. Step two, integrate. All right, so I'm hoping the integral on the left looks a bit familiar from kind of that warm-up we were doing. Notice that your inside function is linear, so you're going to have ln as part of your antiderivative. So antiderive the outer, holding the inner, then divide by the derivative of the inner. Derivative of negative b with respect to b is -1, okay? And then antiderivative of 1/5 with respect to t is just going to be 1/5 t. And here is where you have to have your plus c. If you don't put a plus c, there's no way to gain any more points from here, okay? As soon as you put that plus c down, go find your c by plugging in your initial condition, which in this case is 0, 20. So negative ln of the absolute value of 100 minus 20 is equal to 1/5 times 0 plus c. 100 minus 20 is 80. Absolute value of 80 is still 80. So I'm getting ln of 80 to be my constant. Remember to drop your absolute values if you have a constant, or I should say evaluate it. You only need to keep the absolute values if you're dealing with variables. All right, from there we're going to come back to where we first had that plus c. So I've got negative ln of the absolute value of 100 minus b equals 1/5 t minus c, which was ln of 80. All right, now we want to solve for b. I like to get my logs on one side, everything else on the other. And I also prefer to get this log to be positive since it has what I'm solving for in it. So I'm going to get logs on the right side. Okay, why did I do that? Well, now I can condense the logs using quotient rule for logarithms. Now we want to get rid of ln, that's ln of all of that, so we can exponentiate. Notice I've not dropped my absolute values on the 100 minus b since it has a variable in it. All right, multiply both sides by 80. To drop absolute values on one side, we need a plus or minus on the other. All right, I'm going to subtract 100 and then basically change all the signs of the coefficients. All right, remember we cannot have a plus or minus in our answer as we are looking for a function. So what do? Go back and plug that initial condition, 0, 20 to check. So we've got plus or minus 80 e to the negative 1/5 times 0, so that'll be 0, plus 100, and I need that to equal 20. So what sign makes this a true statement? The negative sign does, right? So final answer, negative 80e to the negative 1/5 t plus 100 equals b. Okay. On your packet, you may have seen I included 2 websites. One is the normal scoring guidelines. Another one is this website here. It's a differential equation solver, and since this is calculator active and open notes, I thought it might be good. You're going to need to know steps, but it may help you at least give you a final answer here. It does do some steps for you, but anyway, it could be a good guide. It's not going to be enough to like spit it all out for you, because you have to sort of know what it's talking about. Also notice I have to use y and x and not b and t. Okay, all right, so that is our differential equations problem. I will see you Monday at 1:30 for Zoom, and then we're going to start our final kind of head towards the AP exam. So be on the lookout for that. Our final 2 weeks will look a bit different, but I think they're going to be very valuable in preparing you for May 12th. All right, I'll see you all on Monday.